Today I'm going to brief about the jacket secondary steel calculation. Apart from the primary calculation, we are responsible to to come up with the secondary steel which are needed for the jacket engineering. So there is lot of items will be covered in the secondary steel calculation based upon the jacket configuration, and then type of installation, and the type of whether it is load out or trailer load out or skidder load out. uh, you know um, uh, uh, Based upon the pre-service analysis and the configuration of the jacket and then the installation of the jacket, these secondary steels may requirement be varying. This is not common, but there is some of the common things which will be coming for all the jackets. So I will describe that for that items. Apart from that, there will be many items will be there secondary on design requirement. We will adding the secondary details to the document actually. So first we will I will show the what are the topics which will we are covering in the jacket. The wave slamming check. This wave slamming check, that the wave slamming where we are checking, where we are checking at the only jacket walkway members, because in the deck we are not checking any wave slamming. The reason, because for the deck, bottom of BOS, bottom of steel elevation, we know that we are giving 100 year storm, plus there will be some air gap will be provided. So however, there won't be any wave slamming on those region. But if there is any wave slam on this region, on the top of the bottom of the steel, if anything is comes in unavoidable situation, yes, we have to perform wave slam for that deck elevation also. Maybe that may be applicable for old platforms, maybe those days, whether if it is not considered, we have to check for that one also when it comes for brownfield, all those things. But most of the cases in nowadays, we are calculating all the data, everything for the air gap, everything, so that the member exposed for the wave slamming check for only the jacket members. So what are the members exposed in the splash zone region? The splash zone region is the wave slamming area. So we have to check the members in that region. Then it is a pile spacer weld check. We know that if it is grouted or ungrouted, there will be a pile spacer inside the jacket leg, and there will be a pile will be inserted in the jacket leg. So there will be a spacer will be there. So each and every framing level, there pile spacer will be provided. So whenever there will be a lateral, this one, no, a lateral force, the lateral force will be transferred to the jacket, and the jacket will transfer to the pile through the pile spacer. So that we will check how we are checking for the how we have to design the pile spacer, and then what to be checked for the pile spacer. And then third one is crown shim. That that is for welded jacket cutoff level. So that the top side is sitting over the top of the pile, and the jacket is wrapping the pile. Actually, there will be, if it is 4 pile, so we are giving the jacket to wrap up the pile, so that the pile will be in position, so that top side will be placed over the pile directly. And so in the interface between the jacket and the pile, there will be a weld at the top. Because in analysis and all, we are considering the pile head on the mud mat, but actual connection is the at the top only, in the crown shim point. There will be no physical fixity on the mud mat level. So all the your jacket load will go to the top weld through the crown shim, and then it will transfer to the pile. For that, there will be some piece we have to provided in the jacket, where the jacket cutoff is there. So that that piece, and then their weld we have to calculate. That is called the crown shim. And then design of closure plate. This one already I explained in the on bottom, when we are presenting the on bottom analysis. Why we are going for this closure plate at the top of the jacket level? We are going for the closure plate in order to achieve the buoyancy. We don't want to flood the leg. We need the buoyancy. For that reason, we have to go for closure plate. Actually, in the bottom there will be a diaphragm plate will be there. It is a rubber kind of thing which will be placed at bottom of the jacket. Once the pile is inserted in, it will be punched through. But where the closure plate at the top of the jacket, where the flood lines flood lines will be there inside the closure plate to flood the leg once after the buoyancy is completed. Okay. Okay, so where we have to check the wave slamming force. See, this is the jacket walkway elevation, jacket walkway framing level here. Basically, this will be in the splash zone. If you see here, there will be two members highlighted. Okay, there will be a lot of members is there. Now the question is whether I have to check wave slam for all the members. And one more thing I will tell, I want to specify here. Already we are checking the members or those regions also wave for particular wave. After the chart datum, we are giving the wave elevation so that the wave height and period. So these members will not attract any wave force, or that like questions you might be having. So to question for that, when the wave force is come, definitely these members will be attracting the wave during the in place condition. That time itself it is checking, means already it's checked for wave. Why I am again I have to check for wave slamming? Yes, there will be a, so all the waves and all will be horizontal load only. So the horizontal load will be captured, but there will be there will be a load when the wave slams. So what happened, there will be a your vertical velocity will hit your member at the bottom, so that you will have one upward force, upward load kind of thing. So for that load, for that water pressure, we have to check the wave slam over here. So that will be the vertical force. So we have to calculate the vertical force through the velocity, and then we have to check for these members. Okay. So now second question is whether what about this member I have to check or no. We have to identify that. So what the here is, we have to use for our engineering judgment here. Because see, this is the member which having 219, 11.1 is the thickness, 219, which is the out of this is the least member diameter, actually least member diameter, and which is the longer span in this framing elevation. If you are taking and checking this one, and if it is pass, then it will sufficient for all the member, it will get pass. And again, why I'm using for this member is, again from the in place analysis, suppose this member is suppose 508 into 19.1. If this is member is there, suppose this member is 0.99 stress ratio in place condition, then we have to include this member also for wave slam check. So 0.99 plus this additional wave slamming force. For that UC, we have to combine this one, and we have to show it's less than 1. If it is 0.99, again if you are adding the wave slam forces over here and then checking for UC, definitely this will be going to more than 1. For that, from the in place result, and then the spacing, and then what is the the length of the member, all those things we have to come for engineering judgment. This will be okay, this one need not to check, like that we have to conclude. And then we have to check for the wave slamming through this region, because we don't know, sometimes if it is 8 leg jacket, there will be a hundred of members will be also will be there. So each and every member we cannot check. For that you have to use your engineering judgment. So these two members it is taken. Okay. Okay, in if you go in SACS, in that there is a current profile you are giving, current velocity you are giving at each and every line in the wave force. There will option will be there for vertical velocity. If you click that vertical velocity, in that output you will get the vertical velocity. So horizontal velocity will give the horizontal force, here vertical velocity will give the vertical. So this vertical velocity you have to take, and there will be a height will be there. If you see here 98.34, 90, there will be elevation here. And from the drawing, you know that where this jacket elevation is there, this member elevation, you will come to know from the jacket drawing or your model also, you will come to know the elevation at the particular elevation. So this is the elevation at 91.43 meter. So this is the elevation 91.4 meter. You have to see the vertical velocity, which will be the this will be the theta angle, this will be the angle. So you have to see which this one, no, having the means more vertical velocity. So this will be 3.52 is the my maximum velocity. So we have to take this velocity for your calculation at this corresponding level. Okay, but if it is 91.3 and 94 93.84, which is very near to this one, if you are having 3.54 somewhere here, there is nothing wrong in it, you can take this one. Whether if it is calculation passes, we can leave it. If the calculation is not conservative, then you have to take for exact this one for conservative approach, I'm telling that. If it is failing, then you have to dig it further. So you have to take the corresponding elevation, what is the velocity. So this is the velocity 3.542. Now we got the velocity at the elevation over here. This is from the SACS output. After that one, so this is the in place you see. If you see here, this is the framing, the same, this is the in place you see here. In the in place you see, this is, if you see here, here I told that if it is 0.99, then we have to check this is 0.37. Anyway, that wave slam will not contribute another 70, 73 percentage of stress, it will not get contributed. Hardly it will be some 10 percentage, maximum 15 percentage only it will get contributed. So if you see the stress ratio for all the member, if you add another point, some 5%, 6%, it won't get affected. But this will be the more slender member over here. And if you check this one, this is 0.46 and this is a 0.35. So for these two members, I'm checking the stress ratio for adding the wave slam check, and then I'm checking the stress ratio. So for that, what we have to do is, if you check for, this is the hand calculation only. This is not a very great calculation and all. Simply what we have to do, no, we know vertical particle velocity from the Morrison equation. You know the how to calculate the load based on the CDCM value. There will be a Morrison equation will be there. So substitute all the parameter in the Morris equation. So whatever the water pressure, upward pressure is coming here, you put it as a load over here, this load. So according to the load, if you put the load, you know the bending moment. If you take, this is the continuous beam. Continuous beam, you know that bending moment WL square by 12 or WL square by 8. You know from the bending moment formula, you can select the bending moment formula, and then shear force you can calculate it from the given load. What is the shear force, and from the sectional property, you know what is the max allowable bending stress, and what is the axial bending stress. From there you can calculate the UC. So if you go to the calculation here, this is checked for 100 year storm wave. So for that, height of the wave is 18.3 and 14.4. For this 3.95, we are 3.542, which we have calculated the particle velocity for that elevation. So here, if you go to here, that multiplied with 1.1, this one 3.542 into 1.1, 10% increase. That is the factor for wave dynamic amplitude. We know that because DAF we are going to be given in the load combination, where the same thing DAF, whatever we are calculated, whether it is 10%, 20%, you just multiply with this velocity. So that's what here we did. The maximum vertical water particle velocity is calculated SACS output as this one. So increased by 10%. So 10% or whatever the DAF it is coming, if it's calculating 1.2 or 12%, so you multiply with the DAF with this velocity. And you know the Morris equation for this one, CS equal to W by 2G into D into U. CS slamming coefficient, you know that 5.5, and this is the mass density of the water. So now here you know the all the parameter over here. CS it is there, and W is there, 2 into G value, you know. D is the this one diameter here, and U is the velocity. D is the diameter that 273, that is the projected area where the water is going to be this one, no, act as a pressure. and u square, u is the velocity here. So substitute all the formula here. So that's why it is given. This is the one calculation over here. See here, this is the 0.219. This is the member diameter here. That is the FW, projected width. This is the projected width, and L is the length of the member, 5.06, and slam force. Once if you put it in this calculation, you will get the 9.6315 kilonewton per meter is the load over here. And this is the M1 and M2, end moment and center moment, because this is not simply supported. The member is running like this, so that we have to calculate there will be a negative moment and the positive moment, means hogging and sagging, M1 and M2. See, we have to calculate the moment at the end and the center. So moment at the end is 20.55, and moment at the center is 10.28. This will be the, you know, that this, what is the center bending moment for the continuous beam, WL square by 12, what WL square by 8 at the end, center 12, like that. So you have to calculate the continuous beam formula. You have to calculate it here. This is the sectional modulus of this section, 219 diameter. From here, maximum bending moment we can calculate here. So 57.8 by maximum bending moment stress here. This is the in place 0.35 and 46, 0.35 and 46. This is the 2 UC. This is UC, and this UC is actual bending by allowable. This is the allowable bending. This is the actual bending. So this by this will give the this is 1.33. We have multiplied over here, because we know that, because this 240 into 1.33, which is 211.5. Why 211.5? Because this is 100-year wave storm, so that we can take the this one 1.33 as a allowable increase in stress, 1.33. So that one we have to multiply. So 21, this is the allowable bending stress. So actual bending stress, you will give the 0.624. This is the in place plus this 0.642 in place plus this wave slam check. So this is the this is contributing some 20% to this. So this will be the UC for wave slam check. If you see, I will show the calculation over here. The same thing only, but it is in calculation. If you, this is the sorry. Okay, this is the for each and every load, 401, 402, 403, 404, 405, each direction you have to check which is the maximum velocity you have to come up with that. And if you go to the calculation here, see, this is the calculation here. If you check, this is the in place, and this is the, if you see here. So this is the allowable, this is the actual bending stress divided by allowable plus this in place. Here it is called here plus this in place. So 0.35 plus this one, this actual by allowable, it is given here. The separate for wave slam alone, it's not given here. If you want, you can we can introduce here due to wave slam, something like that, here to wave slam like that. And again you can calculate one more one more column like total UC, like that also total UC, so that you can have the clear picture how what is the contribution of this one. Otherwise what we have to do, we have to physically minus and see what is the contribution of this the 0.27 is the contribution through the wave slam, something like that. If you want, we can add one more tab also here. So this is the wave slam check for the jacket member on the walkway. This calculation. So here, if it is failing or anything is there, what we have to measure, what we have to take is, we have to break the span over here, so that we have to break the span, and we can consider the L length, the effective length we have to minimize, or we have to increase the section property, so that the bending section property will get increased. Same way you are increasing the load also, the projected area of the velocity will be increasing. So like that you have to go for trial and error, which member will be suit for your walkway, in order to pass the in place analysis combined with the wave slamming. Okay, this is the wave slam check. And next is pile spacer. Okay, pile spacer. We know that pile spacer where it will be there for every framing level. Suppose if you see in this drawing 6.7, this is the jacket walkway level 6.5. There will be a no framing after this top of the jacket because this is a pile cutoff over here. There the top of jacket at the 7.5-meter elevation. There will be a 6.7 to 7.5. There is a gap here where the crown shim will be welded over here. And if you see each and every level, there is a pile spacer. So there won't be any spile spacer, this one in that middle, actually in that middle of the jacket, because once the jacket is deflecting here due to this wave on the horizontal deflection, so the pile has to transfer the load. So this is the nodal point. We should not transfer the loads at the weaker section. This is the strongest section which we are having the lateral frames. For that reason, there will be a no spile spacer provided, means that length of throughout the length of the jacket. So they will provide at the only the means wherever the framing elevation is over there, there only they will provide the pile spacer over here. If you see if you take the section B over here, see there will be a pile spacer is provided. If you can see the some black color representation here, 1, 2, 3, 4, 5, 6, 7, 8. So 8 pile spacer is provided at in the circumferences of the in the inside circumference of the jacket leg over here, actually. So this will be the for every 45-degree they will provide one pile spacer. This is the industrial standard practice over here. We can check the what are the loads over coming here for this horizontal force or vertical force. This is okay or not, we have to check for this spacer here. This is the cross section of the spacer here. If you see here, the spacer is given 490. 490 is the depth of the spacer and 250 is the width of the spacer. And there will be a see if you see here, see actually in offshore they will fight for each each of weld, people will fight for it, actually. So if you are if unnecessarily, see this and all standard thing, if you are giving for for intermediate weld for this one sorry 10 thick plate to the deck plate to the beam, if you are giving more than 5 or more than 5 they will question why you require for high thickness of weld for grating. And when you are giving some standard things, we have to be very careful what we are giving. Suppose in the spacer you note that typically three sides 8 weld. So this side 8 this side 8 this side 8 if you see the top only 5 only is given, so 3 not given. We can think over that why we have to only 5 plus 3 we can put. Now what will be going to happen for this 3 what will happen is there will be a, so they have to maintain that thickness. For that they have to weld, and they have to there will be a we have to supply the electrode for that. So all those things will be there in order to minimize that one. So wherever the necessary only they will go for in offshore particularly, they will very much they will watch how much the weld size you are giving. If anything is not there from the yard, they will comment it you are drawing also why you want this much. You have to give explanation, so you have to be very careful. So for 3 also weld also matter here. So why? Because this weld is not going to be take part any of the calculation here. So this is this entire this shear, the entire length and this length is going to be take part. For that reason 8 is given at the circumference of this perimeter of this one, not on the top. Only 5 is given. And if you see the cross section of this weld, how it is welded. So this one is the jacket leg. This is the jacket leg, the outer one, and inside is the pile body. If you see here 2210 is the id of the jacket, internal diameter, and the OD of the pile is 2133.6. This is the OD. Okay, if you see the annulus between this one, if you minus 2210 minus 2133.6, you will get 37.6 something. So it is round after to 38. 38 is the gap, which is annulus gap between the jacket leg to the pile. So this annulus gap is filled with the one pile spacer at the each and every framing level over here. If you see here, the pile spacer, the thickness of the pile spacer, it is given over here 20 mm. So 20 mm, see this is the 20 mm thick, another 20 mm, 8, if you minus this 20 mm over here, this 20 mm, so that 18 mm, 18 mm is the gap, which will be the, this one, this annulus gap. So this will be there. So there will be no physical contact will be pile spacer to the pile. So whenever there will be a wave, so it will transfer so whenever the jacket deflects 18 mm over here, so it will transfer the wave load over here. Otherwise, it will be the all loads will go there, the top of the crown shim over here, and then basically the jacket will hung on the pile at the top most point over here. Okay, so the lateral load will be transferred at the each and every framing level through the pile spacer. This is the pile spacer detailing. And if you go here, okay, and so here what to check here, nothing is there. We have to check the weld length, whether it is sufficient or not. We have to check. So for that pile spacer weld, so we know that pile. So what the thing is, see from this one, we have to check what is the maximum span of this level. Actually we have to check which is the maximum level. That one we have to take, and then we have to calculate the self weight of the pile over here. If you see, this is the maximum length of the pile out of this all segment. This is the 70 meter. For this 70 meter, we are calculated the dead weight of the pile. So this is the 1364.16 is the self weight of the pile for 70 meter. If you see here, 84 inch and 84 inch, 2.1336 meter, 2.133. Okay, 13. This is the diameter of the pile, and this is the 1.5 inch, which is equal to 38.11 mm. This is 38.1 mm. Okay, over here, and there will be a 50.8 mm, 50.8 mm thickness. So here it is 0.0508 meter. So this will be the thickness. So from here, from that length, we are calculated the weight of the pile. So now weight of the pile segment we have calculated, and the dynamic factor we are putting 1.5 for this pile. So dynamic factor. So design force we know that F equal to W into this one, dynamic factor by 2. This is the load by 2. Why? Because this one we are considering the fact that pile P1 shall hit at least 2 pile spacer at a time. That's why, suppose, see, conservatively only we are designing for this one. See, suppose this is a pile spacer. This is a pile spacer. See, there will be 1, 2, 3, 4, 5, 6, 7, 8. When there is an annulus gap here, when there is a wave here, if you see here, 1, 2, 3, 4. This is the this is the center line of the tubular here. Definitely it will hit 4 for this one. When it is in the wave in this direction, your jacket will hit the 4 pile spacer here, but this pile 4 spacer will not active because the annulus gap is going to be increase it over here. This whatever the 18 mm is going to be increase in this side, so your 4 only will active. So that in that 4-1, we may not know whether this 100% will touch or not, but definitely these two will get touch. For that, this one assumption we are going, at least two of the pile spacer will hit the pile. Okay, I think everybody is following, correct? People are there? Yes.
Yes sir, yes sir.
அவர் இல்லைங்களா சாரு, அவர் போயிட்டாரா? ஓகே.
ஓ ஆமா
தெரியல, அதான் திடீர்னு எனக்கு I have doubt whether all people are moved to some other meeting or same like that, you know, last time. Okay, okay, now you got why we are considering only the 2 pile spacer. So this is the 2 pile spacer. In the 2 pile spacer, 50% of the load has been considered for each pile spacer. So whatever the load, this one divided by 2 is we are considering. That's why W into this dynamic factor divided by 2. So this is the shear load. See, this is 1023. This is the shear load. So this load, the height of the pile spacer we know 490, and the width of the pile spacer is 250. The weld length of the plate, what we have to 490 plus or 250 plus or 490. This is the only we are considering only three phases. If you see here, considering three sides only, welded top of spacer is neglected, because during the shear we know that this and this only contribute will be more contributed here, so that we are considering only these three. Top one we are neglecting. Now we know that the yield strength of the weld electrode, what we are using, 70 ksi. 70 ksi, this is the standard electrode which we are using for the all offshore welding. It is the yield stress is about 480 Newton per mm square. But when we are checking the weld, we have to check, we have to take for this 480. When we are checking for the combined of plate and then weld, then we have to check whichever is lesser yield. Okay, but here we have to take this one because of weld we are checking 480 Newton per mm square. This is the weld electrode capacity, yield capacity. So required of the size, we know that load divided by area. Area is the length of the weld into 0.707 into zero point 0.3. Because we know that because if it is 8 mm weld, we have to take only 0.707. 8 mm we should not take it, because the throttle length only we have to take, the perpendicular length only we have to take. For that 0.707 will come into 0.3 into FU. So what is this 0.3 into FU? For this allowable weld actually. So whatever the shear value, you know that shear for the member, for the tubular, how much you are calculating, you are calculating only 0.5 times of the area of the tube. You know that why you are considering the shear only for that area. Let me explain that area. Suppose this is the some I section. This is the I section. For this I section, what is the area we are considering here is, oh sorry, yeah, okay. So what is the area we are considering here is only the web area. Here we are considering the only the web area. This area only we are considering for the shear calculation. Though there is a weld here, this area we are not considering, because this area will contribute only the flexural, means that it is contribute only the bending. So we are not taking the shear. For the shear calculation, we are taking only the web area alone. We know that even though this area of the I section is something, we are calculating only the area. And also area, the same concept for this. This is also what do you call this tubular also. If this is the tubular, for this is the tubular area between this, this is the tubular area. This is the tubular area. This is the area we are calculating. But here we will not take the full area. Why? Because when they subjected to bending, the same concept here only. In shear, it will only contribute only this area. So if you put a line, this is the area only we are going to, this is the area only it is going to be effective. That is the reason for tubular also we are taking only the 0.5 of the area. Same like that, if you come to the calculation over here, when it is shear area for weld, we are restricting to 0.3 only. We are not going up to 0.4. We are going to up to 0.3 only. So 0.3 into Fu. Fu is this weld. Then if you calculate from this formula, what is the weld thickness required? So weld thickness required 6.79 mm is required. But what we are provided in the drawing is 8 mm we are provided. So hence this is okay. This is safe. So this is the pile spacer and the pile spacer weld. And come to here. This is the pile spacer weld. Okay. Okay. The next one is crown shim. As you know that crown shim will be the physical connection where the means that we can call it as positive connection between the jacket and the pile. That is the crown shim where here. What they will provide it, we know that there will be annulus between the pile and the jacket. What they will put, no, they will provide one, the one one half cut tubular, one plate will be provided, rolled, and then it will be placed, two off or four, three off or four off, based on the rolling, this one, no, fabrication, all those things of availability. Like that, they will come up with the crown shim plate over here. So what they will do, no, this is the jacket cutoff point, this is the pile. So they will place one crown shim plate over here. There will be because we know that this plate will be always will be the site weld only, that only, this is the, the site weld symbol is present here. So this this material preparation and all they will do in yard itself, and they will go for trial fitting and all they will done before this one taking into the offshore. Once after a pile is installed, so this piece they will weld it over here. This is full pen weld, they will weld over at the top and bottom, so that there will be a positive connection at the four leg. If it is four leg, so four leg will be provided. If you see this cross section of this one, this is the section AA, and this is the point. The crown shim piece 75 thick, 300 mm long, this is the 300 mm long. Some case this will be the more than also 500 mm long also will be there, 300 mm. And there will be a weld, so sometimes the weld will not sufficient, this weld length may not be sufficient. For that they will go for some, zigzag kind of plate material, and they will weld it. I will show what it means, how to increase the weld length of the crown shim plate. As we know that we can only weld over the circumference of the weld. Apart from this, how to increase the weld length, if it is not sufficient, the weld length is not sufficient, that we will see how to do that one. If you see the cross section of the pile, if you see the 75 thick pile, so 75 thick, how we have to calculate this one, the 75 thick, we know that from the annulus to annulus 38 mm, we already we saw that. See, yeah, here it is there, 78 mm plus this jacket leg thickness will give the size of the crown shim, the thickness of the crown shim plate. Now we arrived at the crown shim, because once we cannot have more than, projection beyond the jacket leg. Anyway, this is the maximum thickness we can provide. Actually, if this thickness is not sufficient, then we have to increase the height of this one, so that if you increase the height, this one, the sectional property will get increased, so that we can have the crown shim plate. Okay, so this is the weld. Weld is the top weld, and there will be a butt weld is there, and the top of the jacket will be there. Top side is fillet weld, and bottom side is the butt weld here. It will be provided at the circumferential of the jacket to the pile. This is the detail of the crown shim. And if you see the design of the crown shim plate, how we have to take is, suppose there will be a four leg connection will be there. Here, this, see where it is, the work point is there from here, and from here to here there will be some small member will be connecting here. If you see in the our jacket model, there will be a small length. This will be on the four. If it is four leg, there will be a four member will be there. If it is eight leg, eight member will be there. So this is the four leg jacket. If you see here, 801L, 2L, 3L, 4L. These are the member end forces. From this member, we have taken the maximum forces. From this member end forces, we know the axial, shear, X and Fy, Fz, and torsional and moment in plane moment, out of plane moment. So all the forces, these forces we will get it from the member end forces. This can be either 100-year or it will be the 1 year also. Once what we have to do, if it is 100-year, then we have to increase the stress by 1.33. If it is this is governing with 1 year, means we should not take 1.33 only, that's all. Weld connection between the pile and the crown shim. Fillet weld throat thickness, we know that there will be 38 thick over here. So 0.707 into 38, this one. So 26.86. This is the this is the weld what we are given the fillet weld over here. This is the effective thickness actually, effective thickness of the weld at the top, and internal diameter of the weld. Why we are calculating means we have to calculate the weld property here. Internal diameter of the weld 211.3.6. This we know that 211.36 the pile OD. That is going to be your diameter of the weld. So now we know the diameter of the weld. Now consider this is this weld as a one tubular. Like that we have to now calculate the sectional property of this weld. So now we know that dia of the weld and thickness of the weld. From this we can calculate the area of the weld. This is the area of the weld, and this is the shear area of the weld. This is the area of the weld. Shear area we know that 0.5 of the area is the shear weld of the shear. It's considered as a tubular. So 0.5 is the area. And torsional inertia for you know that we know that formula pi into 32 capital D power 4 minus small d power 4. This is the torsional moment of inertia for the circular tubular. Same like the torsional moment of inertia section inertia force is calculated here. Then sectional modulus weld again pi by 32 into d power 4 minus small d power 4 divided by this one 2187. 2187 is the diameter divided by d. D is the section modulus of the tubular. Because here it is weld. We are for that we have to include weld. It's like tubular only, all tubular formula only. Then now we have to calculate the torsional shear stress. Now this one we have to calculate the, see, this is mm power 4. In order to convert this one stress, we have to divide it by mm square. So that area we have to divide it by, then this will be become stress. How to do that one? We know that mx divided by this z, this m by z. We know that from the ordinary bending formula. If you multiply this one with z, you will get the shear stress. What we are going to we have to convert this all the thing to stresses. So shear stress, this moment we know that this is a member end moment, and this ip is the torsional inertia of the weld, and 2187 by 2, this is the y dash. Y dash means the fiber at the extreme end, means that d by 2 means from the center of tubular to the maximum this one outermost fiber of the, what is the stress for fiber. You can calculate the inner stress also, inner fiber also, by decreasing the length of the leverum of the length from the tubular. You can calculate the stress wherever you want. You know that you can you know that if it is this one, no, tubular is there, there is a shear stress distribution, something will be like this, so that the extreme fiber will get the more stress compared to the inner fiber. So we are calculating the only extreme fiber, because that you will have the conservative design for this one. So 7.62 is the stress which will be across the section, section, tubular section. Here it is weld instead of tubular, here it is weld. Here in order to find the lateral shear stress over here, we are taking the resultant stress here, fy square plus fz square. This resultant stress means that this shear stress in fy and fz, this is square root of square into square root of, this will be given the resultant stress over here. This resultant stress over divided by the sectional modulus of weld will give the shear stress. This is the, this one, remember that this is the torsional shear stress, this is the lateral shear stress here. So lateral shear stress we are considering. This is also Newton per mm square. All the unit you have to be in Newton per mm square. This one divided by the sectional modulus. Here we got the lateral shear stress over here. And the resultant shear stress is equal to C. Now this one, now we have, this is the torsional shear stress divided by this inertia will give the torsional, and this is the lateral shear stress. Now we have to combine this shear stress. For that we are taking the 7.62 this shear contribution through the torsional plus shear lateral shear. This two shear we have to add up. So 34.50 Newton per mm square is the total shear here. Now now we have sum up all the shear, we got it. Now we have to go for calculation and we have to calculate the moment. So the same way we are calculating the resultant moment. This one 5265.32 plus this one, this resultant moment we have to calculate it. This is the resultant moment. From the resultant moment, we have to calculate the bending stress divided by Z. We know that 96.68 we are calculated the ZX. See, this is the ZX. If you multiply that divided by that, you will get the bending stress here. And axial stress, of course, there will be one more component also will be there, axial stress. 12074. This is axial stress. So axial stress divided by axial area. So this 181.21. 181.21. This is the axial stress. See, we are not calculating this. See, 181.21. So P by A, this area only, because axial stress, we have to take full area only. Shear stress only 0.5. So axial stress, we have to take full area. So now we have to combine this bending stress, bending P by A. This is nothing but P by A plus M by Z. P by A plus M by Z. This one. Axial contribution plus bending contribution. This is 15268 Newton per mm square. Now we have the bending stress and shear stress. Now real resultant stress in the weld. These axial stress and the bending stress combinedly going to act over here for this weld. For that, we have to take resultant of, sorry, okay, we have to take resultant of this 152.68 square, this one, plus 26.68. 26.68 already we have calculated here. The lateral shear, all the shear we are combined up here, 26. So this one 154.99 Newton. This is the stress in weld. So this is the actual stress. Now what is the allowable stress? Allowable stress equal to 1.33. This is the 100-year force. This is the 100-year storm force over here. We are taken the 1.33 into 145. 145. Here there will be a question why it is 1.5 193, because we know that here what we are doing is 483 into 0.3 fu. See, in this calculation already here we are taken that. See, 0.3 fu. So 0.3 only we are taking here. Why? Because here is the shear also we are taking into account for that. So if you multiply that one 483 into 483, because we know that this 70 electrode KSI is 483 into zero point 0.3. It is coming 144.9. 144 is nothing but 145 into 1.33, which is 192. 192.7. This is 193. So the fraction is it is taken here 1.333, something like that. So it is 193.3. So the actual is 154, actual 154.99, actual by allowable 193.3. So UC of 0.8. Now the weld is okay. So this is the crown shim check, weld check here. Suppose the crown shim is not passing over here. What we have to do? So suppose this is some this is suppose 130, allowable stress in 130 only, but actual is more, actually 144.9, and this is more. Then what we have to do? No, see where we can correct. There is only one clue we are having. Where means if you correct this area of the weld, if it is this area of the weld is increasing, this will be get increasing. This term will get increasing, this area will get increasing, all with subsequently this all value will get increasing. Your allowable, the actual value will go lesser. For that, how to increase the weld size? If you see here in the next slide, if you see the bottom of the weld, only the circumferential weld. If you provide instead of the going for circumferential also weld here, what they will do? No, they will provide this kind of profile over here. Now your weld length will get double almost. See, it's coming like this, going like this. So all the weld length is getting increased. So that weld length you have to take, and then we have to again calculate the stresses. Okay, definitely with this one, this will be getting solved over here. So we can so that the design of weld is sufficient for the crown shim. Okay. Okay, now, okay. Okay. Now closure plate design. We know that this now closure plate design. As I told, the closure plate will be provided at the top of the jacket. So if you ask each and every jacket will have closure plate, no, based on requirement. When you want to take advantage of the, if you are not having the flood capacity of the jacket, when it is flotation, then you have to go for this closure plate. Then you have to take the advantage of your leg to be buoyant. For that reason, we have to go for closure plate. This closure plate will be there on each leg. If it is 4 leg jacket, 4 legs will be placed. If it is if it is 8 jacket, 8 leg jacket, this closure plate will be placed. Basically, once if you are going for 8 leg jacket, most probably they, because of you will not have enough buoyancy over there. Because of 8 leg jacket, you need more positive buoyant over there. For that they will not go for closure plate, because for that, if you put closure plate also, you will not have the sufficient buoyancy. They will go for buoyancy tank. Once if you are having buoyancy tank, there no need of closure plate here. We can flood the leg so that the buoyancy tank will be there. So you will have the enough buoyancy through the buoyancy tank. But if you want to effective design, and if you want to minimize the buoyancy tank, then you have to go for closure plate as well as the buoyancy tank also. For that reason, you have to put the closure plate here. If you see the closure plate, this is the like plate. There will be a one flat plate. Suppose if you see the flat plate, so 20-25 thick flat plate will be there. On top of to that, there will be some section, angle section or a cutty section will be placed over here. Why? Because this closure plate, sometimes if you are having this much of span, this will get bent. In order to avoid that one, they will go like this, will be like stiffener only they will go for. And there will be a flood valve also will be there. After placing the jacket on the seabed, if they want to flood through this hole only, the leg will get flooded over here. The connection between the leg and this closure plate, the weld will be given. See, fillet weld will be, see, I will just tell the one more clue. All the temporary item will be fillet weld only. Mostly 99% they won't go for any full pen weld. Why? Because full pen weld is the very laborious process. So 12 thick weld is given at circumferential to this closure plate over here. We go for calculation here. How to calculate this curve? So this one closure plate here. What is the force is going to be act when this jacket is launching or anything? We know that there will be a the pressure, the water pressure will be depend upon the head. Whether if you have more, if you go at the surface to the bottom of the sea, when your water head increasing, your pressure will get increased here over here. So that the length of the jacket where this closure plate is going to be subjected, that much of height you have to take. That much of height, that pressure you have to calculate the water pressure. We know that how to calculate the water pressure here. Simply length into that gamma. Length into gamma is nothing but the unit weight of the water will give the pressure, water head. Same like that, hydrostatic design head is 71.3 meter. This is the closure plate at the location. Hydrostatic pressure is 71.672. This is, I will just show the calculation. I will explain from there. You will know better actually. If you go here, if you take the closure plate. Okay, if you see here, this is the hydrostatic head. I think you are able to see the Excel calculation. Correct, no?
Yes, yes, I can see.
Okay, right. Okay.
Sir,
So,
KK, sir, yet to join. Shall we keep continuing or shall we stop here and maybe afternoon shall we join like the other day?
no, ma'am, this is the only one sheet. That's all. This,
Only one sheet left.
uh,
Okay. Okay, sir.
okay. So this is the, if you see here, this is the hydrostatic head and this is the hydrostatic pressure. This is nothing but this length into this head, water head into this 1.05 is the density of the water into 9.81. This is for conversion. 1000 is the to convert the into kilonewton. So this one the force we are calculated here. closure plate diameter and E value. E value 2.1 into 10 to the power 5 Newton per mm square. This is still E value. Then check for plate. We have to check for this plate. We know that here there is a plate over here. We have to check for this plate. Okay, for this plate, so spacing between the stiffener length is 500 mm. It is taken. How it is 500 mm? If you see here, here it is closely spaced 396. Here, if you see here 250, 250, so 500 center to center. So this is the longer span. So this from here the pressure is calculated and then applied the load in the plate, and then we are checking the plate like same secondary beam calculation. So this is the one. From this bending moment, WL square by 10 we are taken because there will be a fixed end moment will be there. This is not simply supported. So W into L square by 8. If you ask here why can't I can go for WL square by 8? Yes, you can go that because it is here that is a fully designer choice only. Here we are having the weld here. Definitely there will be a negative moment here. In order to reduce that moment, so we are going for this formula WL square by 10. We know that from the engineering judgment and what is the appropriate formula, we have to know that. So from this formula, we calculated the moment. Then this is the sectional moment. You know that BD square by 6 for this one. So for we are calculating the sectional modulus for this plate. So for this 1 meter width of plate we are taken. Then allowable stress, we know that for bending 0.5 into Fy, 0.5 into 0.75 into Fy, bending 0.75 into Fy. Fy is 345. And this is a actual bending we know that m divided by section modulus m divided by z. We got the actual bending moment. We know that section modulus from the bending moment equation, bending equation, we know that the actual bending is here. Therefore stress ratio is actual by allowable is 0.66 is less than 1.0. Now we are checked the plate here. Now we have to check the cutty section here. Here we are provided the cutty. This T we are taken UB 457. From there we are taken cut here. Whenever we are giving the cutty section on the plate, we used to take the effective width of the plate also, so that this will be behave as a I section. So that we know that for most of the helideck design and all, we used to take. Sometimes we will give the channel over here. Sorry, angle over here. For this angle, we will take some effective section. It will be some J section like that. We will calculate the section property. Same like that. Here we are taking the I section. Even though it is half cut T, we are taking as the I section by calculating the effective width of the plate contributing to the combined effect of this section. So, so this is the span 1752. 1752 is the diameter. Here we know that. See 1758. This is the diameter. After detecting this weld, this inner weld, this that thing, all those things. Because jacket dia is 1758 minus this thickness, it will be having the effective span. So that effective span is calculated like 1752. Here it is there. Minus 2 into 44.5. 44.5 is the thickness of the jacket we are taken, and area we are calculated from this. This area is the we have to calculate. As I told, we have to take the I section. This is the I section. How much the effective width of the plate we have to take is there is a formula here. If you see here, effective width of the plate 0.38 into square root of E by Fy into 2 into T. This is the formula to calculate the effective width of the section. So UB 457, we know that the width of the top width of the plate and bottom width of the plate we have to take the calculated from the effective width 468. From this like I section we can calculate using any section property tool. Area, whatever the required IXX, IYY, ZXX, ZYY, and torsional if you want, we can take whatever. Because here we are going to check only for bending. That the reason I have calculated for only the IXX and ZXX. Okay, then load. What is the load on this one? We know that there is a pressure of this is the pressure hydrostatic pressure 714.71. This projected area 71.71, we can, this is the length of the the width of the top flange we know, and the length of the flange we know. This 717, this is a 17152. So this one, this projected area into this hydrostatic pressure will give the total load. Total load divided by this span length will give the per meter load. Okay. From here, the same thing only. If you select this one, this width and this length is calculated, and then with load, linear load is calculated, and then WL square by 8. This is we are taken as a WL square by 8 because there will be only weld and this because there is no support, intermediate support here. We are taken WL square by 8 from this bending moment calculated. From here, bending stress is calculated 0.66 Fy. From the this is the allowable bending stress. Actual bending stress we know moment divided by this ASXX. It will give the moment divided by this ASXX will give the actual bending moment. So actual by allowable will give the effective stress ratio for the member. This one. Now this is 0.28. Now we checked the plate and the section also on top of the closure plate. Now check for peripheral weld. This weld we have to check. This periphery weld. This weld we have to check. How to check that weld? So we know that this pressure is 74.71. This weld, this is the pressure where we are calculated the from the water head. This is the area, circumferential area of the plate is the circumference, that is the area of the full area of the weld. For pressure on the force equal to this area. This is the area into this force. So that meter square will get cancelled. Will get only the load kilonewton. So this is the load we got it now. Once the load we got it, we know that stress equal to load by area. We know that formula, a basic formula. Stress equal to load by area. Load we have divided by area. Area means what area? Weld area. Weld area is what is the formula? 0.707 into thickness of weld. That will be the stress. Here, stress also we know that stress, how much stress? The 0.3 into Fy into throat thickness. This 0.3 into Fu electrode, that 483. So if you bring this unknown parameter this side, we come to know this the what is the allowable force. We can calculate all the things, keeping the every all the things we know that because 12 mm weld we are given that all parameter we know that we can check the weld size whether it is 12 is okay or not, or we can check the load also because here all parameters we know that any one thing we can keep unknown and then we can check here. So here 1742 is the actual load over coming here, but the weld can take up to 644.12 kilonewton the weld can take. So that this will be finishing the weld check here. So we checked the plate, section and weld here. So this is the closure plate design. Apart from this, as I told, there will be a many component will be there in the in jacket based on the configuration, based on the yard requirement, based on transportation. For each and everything, there you will be experience different checks and different problems. So you have to apply your engineering judgment, and then you have to combine with you have to come up with some calculation. So all the calculation, the manual calculation, you have to follow the only two is there: bending equation and shear equation. You have to check for bending, shear, bending, shear. If you see the all the calculation, it is calculated in that fashion only. If you check for all the crown shim design to all the spacer plate, here what we checked, here we checked the shear and we checked the length of the weld here. If you go back this one, what we have checked, we have calculated the bending moment. From the bending moment sectional model, see we here we have calculated the UC for bending. For this bending equation only we are used WL square by 8. Here also the same thing, shear we are used. And if you go to this crown shim calculation also, here this all the force converted into shear and moment. With the shear and moment, by combining this one we are checking for this one. So everything lies in between P by A plus M by Z only, the bending equation only, and the shear we have to V by BD we have to take, and then all the allowables we have to know that 0.6, 0.75, and the bearing, if it is something bearing is coming, then we have to check for the bearing stress. All those things we have to check. See, if you want to check in this, if you want to detail, this is the enough for this closure plate. Since if you want to check the bearing stress, you can check. See, whatever the load imposed on the top of to the closure plate, So the area what this is bearing, that bearing area into whatever the force is coming over here, throughout this one you can calculate the bearing stress. And then the bearing stress, what is the allowable bearing, 0.9 into fy, that stress also you can check here, you can include in this calculation. There is nothing wrong in it. Whatever in your mind it is coming, you can elaborate your calculations. So it is not limited to only this one. So the force flow and the what is the thing, you have to think out, and then you have to come up with the calculations. So once you you have the free body diagram and your basic is very clear, you can able to perform hand calculations very simple. Even the skid, for equipment, all those things will be the same thing. Only thing you have to think, if it is moment is going here, where this moment will transfer, what to check, like that you have to think, and you have to come up with some calculations. Okay, so this finished the jacket miscellaneous calculation. If you have any question, please, you can ask. So I will start.
Nothing.